part of this problem, we want to find the expressions or the equations for the electric field inside the insulator, between the insulator and the conducting shell, inside the conducting shell, and outside the whole thing. So let's start with inside the insulator. I'm going to draw my picture again. So part B, and we're trying to find the electric field for R less than the radius of the insulator. So here's the insulator. Here's my conducting shell outside. It's a thick shell, so we can draw it with some thickness. So there's my thick shell outside. So if I want to find the electric field inside the cylinder, I need to draw a Gaussian surface inside the cylinder. So I'm going to draw a Gaussian surface that's a cylinder, and it's entirely within the insulating surface. So there's my three-dimensional view. My two-dimensional view would have my insulator right here, my conductor out here, and my Gaussian surface right here. So there's the two-dimensional view. Let's write down Gauss's law, because that's our first step in calculating the electric field. So Gauss's law says that the net electric flux through any closed surface is the integral of E dot dA equals the net charge enclosed by that Gaussian surface divided by the constant epsilon naught. Let's deal with E dot dA first. So if we have cylindrical symmetry, then the integral of E dot dA is equal to the integral of E times dA times the cosine of the angle between E and A. Our electric field points out everywhere. I think I'll draw it here. And the area vector, a little area element on our cylindrical surface, also points outward. So the angle between those two guys is 0, so this is equal to 1. It's the integral of E dot dA. If our cylindrical surface has a constant radius, the electric field will be constant, so E comes outside, so E times the integral of dA, which is E times A. A means the area of our cylindrical surface, and the area of a cylindrical surface is 2 pi r times the length. That little r means the radius of our Gaussian surface, so r here, little r here. Our insulator has radius capital R. Let's not get confused with our symbols. So let's put this together with this, get an expression for our electric field. Oh, I dropped my E over here. So E times 2 pi r times L equals Q in over epsilon naught. Solve for E. E equals 1 over 2 pi epsilon naught times Q inside times R times L. Okay, so now if we can use this result in the rest of the problem as well. So if we want to find our electric field, the question is how much charge is inside that Gaussian surface? So the amount of charge inside that Gaussian surface is going to be the charge density times the volume of the Gaussian surface. So we've got the charge density, the volume of the Gaussian surface is the volume of this cylinder. The volume of that cylinder is going to be its area times its length, pi r squared, little r because that's the radius of the cylinder, times the length L. So we'll put that for our Q inside and we'll get our electric field. We see that our L's cancel, and one of those R's cancel, and that pi cancels. So there's our electric field inside the insulator. Okay, and then for the direction of that electric field, it would point outwards because the charge is positive. So E equals rho times r times 2 epsilon naught out. And this result is for r less than or equal to r of the cylinder. Okay, now the next one says find the electric field in the area between the cylinder and the conductor. We'll do that part next. So for that part, let's redraw our picture again. This time I'm only going to do the 2D view. So here's our insulating surface. Here's our conducting shell. Again, in 3 dimensions, these are cylinders and shells surrounding each other. If we want the electric field, this distance is R, this distance is Ri. If we want the electric field somewhere in here, we draw a Gaussian surface, that's a cylinder with radius R in between the 2 radii. We'll use the result from the previous part. So from the previous part with the cylindrical symmetry, we started with Gauss's law, we found the expression for E dot dA, and we used that to find the result that electric field was 1 over 2 pi epsilon naught Q inside over R times L. So let's use that result again. So E equals 1 over 2 pi epsilon naught Q inside RL. So we'll say that's from previous. So Q inside is the hard part. How do we find the Q inside? Well, Q inside is whatever charge is on the insulator. Because we ask what thing or things inside the Gaussian surface have charge. The only thing inside the Gaussian surface with a charge is the insulator. All of the insulator is inside, so the charge comes from the insulator. So that's going to be charge density times the volume of the insulator. So density, the volume of the insulator, is the area of the insulator, pi r squared, times the length. So that goes in for our charge inside, then we can find our electric field. So our L's cancel. This time the R doesn't cancel because we don't have a little r on top. Equals 1 over 2 pi epsilon naught rho pi r squared over r. So this is still a positive, so our electric field points out. E equals 1, oh, and the pi's cancel too. 1 over 2 epsilon naught rho r squared over r outward. Okay, so there's our electric field in between the 2 structures. The next part is what is the electric field between this distance and this distance. So Ri less than little r less than r for the outer surface. Let's quickly draw that again. So here, draw our Gaussian surface. This time the Gaussian surface is inside the conductor. So here's our little r this time. There's the radius of the inner surface of the conductor, radius of the outer surface of the conductor. For this part, the electric field is 0 because it's inside a conductor. So that part is easy. And now for the last part, we'll find the electric field outside the whole thing. So let's do one last picture to put in our insulator, our conductor, and our Gaussian surface. So R greater than RO outside everything. Here's our insulator, here's our conductor, and our Gaussian surface is a cylinder outside of everything. It has radius r. We'll go straight to our result from Gauss's law. That gives us the expression we found for the electric field. So E equals 1 over 2 pi epsilon naught Q in over r, radius of the Gaussian surface, times L. From previous, we found that in the very first part. So then the big question is, what is the charge inside the Gaussian surface? So Q inside the Gaussian surface is whatever charge is on the conductor plus whatever charge is on the insulator. So we add up those 2 charges, and then that'll give us the net charge. So the charged objects inside our Gaussian surface are the conductor and the insulator. So we find those net charges and we can add them together. To find the charge on the conductor, we know the charge density lambda. We multiply that by the length and we get the net charge on the conductor. So there's the charge on the conductor. The net charge on the insulator is, and we did this in the previous step, is the charge density of the insulator times the volume of the insulator. So then this is our net charge inside our Gaussian surface. Let's put that in over here and find our electric field. We see that our L's cancel, and then we can find our result. So here's our electric field. If we put our numbers in, we'll see it's negative, so we'll say inward. Okay, it depends on the size of lambda and rho, and the way these work out is that the net charge is negative. So because charge negative. Okay, now to finish up this problem, we want to actually calculate the electric field at some different spots, and then we'll draw a graph of the electric field. So we'll do that in the next part.